Okay, so this is lecture 11, and we're going to talk about the kernels and the kernel trick and high-dimensional embeddings. So the basic idea is that we want to take linear methods and turn them into nonlinear methods. So this includes linear classifiers, but it also includes other linear methods like linear regression and even k-means and PCA. Those were also linear methods in that they applied linear transformations to our data in some way or another and then evaluated the performance of the linear transformation based on a loss. So let's think about the classification setting, the binary classification setting, where we have pluses and minuses represent data points. And if we have a data set that looks like the thing on the left here, then we can imagine that we would like to create a linear decision boundary, and that a linear classifier would do quite well for this data set. But if we saw something like a data set on the right, where the pluses are sort of concentrated toward the origin and the minuses are away from the origin, then we could imagine that we would want some sort of a nonlinear decision boundary, which is represented by the purple line here, where everything on the outside of the decision boundary would be labeled as a minus, and everything on the inside of the decision boundary would be labeled as a plus. So that's where we want to get to, and there's actually a simple way to create nonlinear decision boundaries with linear classifiers, and that's using high-dimensional embeddings. So this is something that you should be already familiar with. You've already taken your data points and then applied transformations. Like for each column, you've taken its log, you've taken the square, the cube, and so on. So you've already probably done a lot of high-dimensional embeddings before. So this should be nothing new, especially for you. So a high-dimensional embedding, what does it look like in math? Well, for some reason this is gone. Okay, so for our high-dimensional embedding, the idea is that we're going to construct some, let's make this black. Okay, so we're going to construct some phi function that is predefined. So we're going to start just by thinking of a high-dimensional embedding is just some phi function which maps our feature space, which is Rp, into some Rd, which this is typically D is greater than P. Right? That's sort of typical. So what are some examples? So an example is that phi of x1, x2 is equal to the vector 1, x1, x2, x1 squared, x2 squared, and x1 times x2. That's an example. Right? And then the basic idea is that if one uses the data, which is zi is equal to phi of xi, then the decision curve, which let's call it beta transpose zi beta transpose zi plus beta naught, this being equal to 0. This is our boundary, our linear decision boundary, and z is nonlinear is a nonlinear curve in the x space. Right? Just because this phi is possibly nonlinear in x. So we've applied a nonlinear transformation to our xi, which we do this all the time when we're constructing features by hand, and this is no different. So we're going to imagine constructing applying this phi transformation. And to see what this would do for the data set we imagined here on the nonlinear decision boundary side, if you applied this transformation, then you could look at x1 squared and x2 squared along those two dimensions, and the data would then, let's see, where are we? Okay, then our data would look like the following, which is our x1 squared is on the x-axis and x2 squared is on the y-axis. You know that x1 squared plus x2 squared is the distance from the origin squared. And so if we wanted a decision boundary which had our distance from the origin equal to a certain point, so that would create a circle, that describes a circle in the original space, well, that would just be a line in this high-dimensional embedding space. Right? And so we could separate this data now with a linear decision boundary after we've done this high-dimensional embedding. So this is the basic idea for how we're going to construct nonlinear decision boundaries from linear decision boundaries just by using high-dimensional embeddings. Okay, so far and so good. So another example I'd like to talk about, which is a good motivating example for this problem, is the XOR function. So the XOR function, the basic idea is that we would like to be able to learn certain logical propositions. Right? Okay, so what is a proposition, and how can we think of this as a classification problem? Right? Okay, so this is a bit counterintuitive because there's no randomness inherent in these data in terms of in this data set at all, right? And so imagine that you were given a data set which is a bunch of a data set which is some x1s and which is in the set true false, right? Which we can encode as a 1 and a 0, right? And x2 also is in the set true false, which we're also going to encode this as a 1 or a 0. Right? So you can imagine a problem where you don't really know what logical proposition you're working with. So you might be working with, for example, x1 times x2, or sorry, x1 and x2, right? That might be your logical proposition that you're working with, but we didn't know that this was the logical proposition, right? So this is p1, x2. So the way that we try to determine whether we're working with and or not is just by plugging in our data. And our data are just plugging in possible values for x1 and x2. So we could try, for example, so for x1, we could try true, right? Or let's make them both false. So let's just go down the line. So both false, x1 and x2. This is equal to 0 because it's also false. x1 being true and x2 being false also gives us a 0. A 0, 1 gives us a 0, and a 0, 0, and a 1, 1 gives us a 1. Right? So this would be our table that would completely describe the possible inputs for this proposition. Right? And if you think about x1 and x2, then we could create a linear decision boundary if this was our data. So this would constitute our data, where this is our response variable y, it's binary, and this here is our predictor variable, our feature vectors x. We could imagine constructing a linear decision boundary which just isolated this this 1, 1, 1 point. Right? But a different logical proposition, which you can't separate using a linear decision boundary, is x1 XOR x2. And what XOR is, it's just x1 or x2, but not AND. That's all XOR means. And so if we think about the data that we would use to learn this, we would have a 0, 0 would produce 0, 1, 0 would produce a 1 because OR is true and AND is not true. A 0, 1 would produce a 1, and a 0, 0 would, oops, sorry, made that same mistake. A 1, 1 would produce a 0 because we do not want AND to be true. So this is just the definition of XOR. It's OR but not AND. Right? So suppose you're confronted with this data, right? The XOR function. And so because you're confronted with this data, you are now tasked with we're done with this. Sorry. Still figuring out how to use this. You are now tasked with, okay, there we go. With coming up with some high-dimensional embedding that could then learn XOR with the linear decision boundary. So let's plot the XOR data. That's what's on the left-hand side here. We have the trues in the are the 0, 1 and the 1, 0. That's when XOR is true. So I'm going to put a T next to 0, 1 and 1, 0. But it's false at 0, 0 and at 1, 1. XOR is false in those cases. And so so you can imagine that you try to separate these with linear decision boundaries and you would fail. Right? You would try and fail to separate these the trues from the falses with just a single linear decision boundary in the original space. But imagine we did the following high-dimensional embedding. We just took x1 and x2 and then also added in x1 times x2. So if we added in that extra feature x1 times x2, then we could imagine plotting our x1 times x2 against x1 plus x2. Right? And the intuition here is that x1 plus x2 is sort of representing OR, right? Because if x1 plus x2 exceeds 0, then OR is true. Right? And x1 times x2 is sort of representing AND, because if that exceeds 0, then AND is true. Right? And we want OR but not AND. Right? And so if we plot our data in the space which is, this is a subspace, this x1 plus x2 against x1 times x2, this is a subspace of the higher dimensional embedding space. Right? Then if we plot this data, if the data points all become the following. If x1 and x2 are both 0, then x1 plus x2 is 0 and x1 times x2 is 0, and a false lies at the origin here. Now if only one of them is true, then x1 plus x2 is 1, but x1 times x2 is 0, and so you get this true at the 0, 1 coordinate. Right? But if x1 plus x2 is 2 and x1 times x2 is 1, or sorry, if x1 and x2 are both 1, then we get that we're up in this following coordinate up here, and so we have a false up here. And so this is a way that if we were given the data, which is all possible possibilities of x1 and x2, just being booleans, right? If we were given all possible combinations of x1, x2, then we could separate out these data points with a high-dimensional embedding that we just described here. x1, x2, x1 times x2. Right? It's a simple high-dimensional embedding. Right? Okay, so this is a way that we can turn our data through a high-dimensional embedding into something that's linearly separable, which is this case of XOR. Now, one thing to note is that XOR was an interesting example. There was nothing random about this. The thing that we're focusing on right now is the approximability or the separability of our data. We're not and sometimes we call this approximation guarantees, and we're not really focused on the ability to denoise. And it's important to know that this drive towards nonlinear methods is driven mostly by the ability to approximate complicated decision boundaries. And to get at complicated decision boundaries, it's not so much. And one thing that we might suffer from is a harder statistical problem. You can imagine that if you're in higher dimensions, you're going to need more data to learn your decision boundary. And so that's going to be the trade-off, is as we go to higher dimensions, we're presumably going to require more data to learn our decision boundary, the desired decision boundary. And that's either if we have noise in the y variable given x, but also just because we have a limited number of samples in the x space as well is going to cause this problem. Okay, so what does this have to do with kernels? Well, we'll talk about that in the next video. It turns out that kernel machines can be always thought of as a high-dimensional embedding, and vice versa. High-dimensional embedding and applying a linear method to it can be thought of as a kernel machine. And so there's this equivalence theorem here, and we're going to exploit that fact in the next video.